All right. Sort of follows a similar formal style to Lang's conjecture and the Mumford conjecture. But the proof method we've been exploring doesn't work so much. You need something else. So I want to explain, first of all, sort of the picture and why things don't work quite as well. Let me focus on the case of modular curves first. Okay. All right. So we're going to start with the upper half plane, which is a set of complex numbers, so its imaginary part is positive. And there's an action of SO2R on the upper half plane. Wherein a matrix takes an element Z to AZ plus B over CD plus D. You can also put GO2R here or PGO2R. I like SO2R though, I think it's not the right thing to select. And so one nice way to think of this action is you can think of SO2R as sitting inside SO2C, and you can think of the upper half plane as sitting in the projective line. These are both under the natural inclusion. And then this action becomes a subset of this action. We're now SO2CX and P1C just in the obvious way. P1C is a complex line in C squared, and SO2C X on C squared. Okay. SO2C does not act in the upper half plane because it doesn't preserve it, but SO2R does preserve it. So this action is like a subset of this action. All right. Now you can restrict this action to SO2Z. And if you do that, then SO2Z acts on the upper half plane discretely. So one sort of very, very quick way to see this maybe, proof sketch, you haven't seen it before, is that if you look at the imaginary part of AC plus B over CC plus D, what you get is the imaginary part of Z over the norm of CZ plus D squared. Okay, so if you don't want this going to 0, then C and D have to stay bounded. And then if you don't want the x coordinate going to infinity, then B has to stay bounded, and so that's the proof. Okay, there's countless proofs of this in the literature. So more sort of concretely and pictorially, let's just keep it 2 pi I over 3. And here's e to 2 pi I over 6. Anyways, you have this famous sort of nice fundamental domain. We take this sort of circle around 0, radius 1, cut it off at these 2 points. These lines out to infinity. So call this F. So F is sort of points, sort of Z equals X plus IY, where absolute value of Z is at least 1. And the real part of Z is between, let's say, strictly minus a half and a half. I think that's enough. Hence, then F is a fundamental domain. For S to Z acting on H, so every point can be brought into this domain in a unique way. It gets a little awkward later that you sort of can't take F to be open, you can't take F to be closed. You gotta be a little careful with that. But it's not actually a big deal. It's just sort of an annoyance. Okay, now if you look at the upper half plane, mod SO2Z. So because the action is discrete, you get a complex manifold, you get a one-dimensional curve. And what you get is actually, so this is a Riemann surface with sort of one point missing. Sort of at infinity. And what this means is if you use the coordinate, so if you restrict here, if you restrict to the imaginary part of Z bigger than 1, then a holomorphic coordinate becomes Q, e to the 2 pi iz, because if you translate by 1, Q doesn't change, so it's exactly a coordinate downstairs. And then there's a coordinate, and the point Q equals 0 is missing. Then usually you call y1 the actual quotient, and x of 1 would be natural objectification of the quotient you get by adding it infinity. And then from this picture is easy, if you compute the Euler characteristic, you get -2. And so it follows from that the genus of x1 is 0, and so x1 is isomorphic to p1. Okay? Complex numbers. And so you sort of think of this as being analogous to the exponential map. And normalize a little bit. Going from C to C star, where you have sort of one algebraic variety mapping to another one with a certain discrete modular group, and they have two different algebraic structures downstairs. It's a little different because the upper half plane is an action algebraic variety, it's just an open set in an algebraic variety. And the group SO to Z is significantly more complicated than the group Z. But this is sort of the way to keep the formal analog in your mind. Okay. Alternatively, you can also think of the abelian variety case we've been discussing as sort of, you have an abelian variety, you have its universal covering space. Here, you get some power of Z as a modular group. Okay? All right. So you can also think of y1, as we talked about before, as the moduli space of complex elliptic curves. So here I should add the word coarse because it doesn't behave very well in families and elliptic curves have automorphisms. Nonetheless, for every point of y1 you get an elliptic curve and vice versa. And before what you do is send the point z to c mod 1 comma z. And then give us a more explicit isomorphism between y1 and the complex numbers. What you can do is you can take the J invariant which takes a point z to the J invariant of the elliptic curve corresponding to z. And because you get one J invariant for each isomorphism class of elliptic curves, these are the complex numbers, this map is actually an isomorphism, and you can extend it to an isomorphism from x1 to p1. Okay, and the sort of good thing about expressing it this way is that this gives you some sort of actual rational structure. So if this elliptic curve is defined over some subfield K of the complex numbers, or let me say of Q bar, maybe. Then the J invariant is also defined over K. Just because you can literally write it down to coefficients. Okay? So this gives a Q structure. A natural Q structure on x of 1. You can think of it as an algebraic variety over the rational numbers using J as a coordinate. Okay? All right. So we're going to talk about some sort of analog of Mann and Mumford. So it's a little similar because we still have the sort of group action and SL2R sort of hanging around in the background, but it's also a bit different because we can't literally talk about sorting points anymore. But there's still a notion of special points, and these are the CM points. So we say that an elliptic curve E over C has complex multiplication, or CM, if the endomorphism ring of E is bigger than just the integers, so you can do more than just multiply. You always contain the integers, but if it's a little bigger, then you can get E and CM. Now it's not hard to see that all endomorphisms of C mod some lattice come from just endomorphisms of C, which happen to preserve the lattice. So it turns out that EZ has CM is actually equivalent to Z. So Z is in the negative plane. So Z being an algebraic number, and in fact the degree of z over q should be 2, which has to, for z to be a quadratic irrational. Okay? So equivalently, q of z is an imaginary quadratic field. Now, sort of one nice, very elementary fact is that the set of z in the abelian plane of the complex numbers, such that this is true, this set, this cardinality, countable infinity, cardinality of the integers, which in particular, and so this is true, and also this set is Galois stable. So the set J of z is stable under the automorphisms of C over Q, because this sort of property is algebraically defined. It doesn't actually care about the analytic structure of the complex numbers. So you have some countable set which is stable under the Galois group, which means that set is a subset of Q bar. Right? Because any transcendental number is the same as any other one under the automorphism group. So this implies that if E has Cm, then J of E is an algebraic number. We're going to use and need much more in the proof, but it's kind of nice to know these sort of soft arguments, right? So let me sort of repeat the argument. So we know that an elliptic curve is determined by J invariant, and if an elliptic curve has a non-trivial endomorphism, and it's defined over C, and you apply any automorphism to it, you get sort of the same elliptic curve, which is defined over the same field embedded to C in a different way. And so this property is still going to be true. So the set of all such elliptic curves, or all such J invariants, is a countable subset of the complex numbers, which is stable under this automorphism group. So you can't have a transcendental point, because then it would have all transcendental points, and that's an uncountable subset. Okay. This is our first sign that sort of Cm points might be somewhat analogous to Trojan points. These are these natural things found over Q bar. Okay, so this will be our analog of special points. Now we define our special subvarieties. Okay, so there's a natural variety inside y1 squared, or rather inside x1 squared. So let me introduce it this way. So first of all, if we take gamma inside S of the Z to be a finite index subgroup, then we can look at X of gamma. Well, we can look at, sorry, let me define Y of gamma first, which is the Riemann surface H mod gamma. So it's a finite cover of Y of 1. And then we can compactifying it by adding as many points of infinity as we need. Okay. So now, a standard sort of, there's many standards for gamma, all coming from sort of congruent subgroups. So we can define gamma naught of n in the set of A, B, C, D in SL2, where mod n is upper triangular. Okay, and then we define y naught of n and x naught of n to be the quotients by gamma naught n in particular. Okay, this is some finite cover of x naught 1. And then if you, so this is x naught n and y naught n without the bar. And so then y naught n has a nice additional property, which is y naught n. It is a moduli space of elliptic curves E plus a cyclic subgroup G inside the n torsion of E. Okay? So it actually goes remoting out by slightly less, so that we keep track of this extra information about the elliptic curve.
And you want to say that this subgroup has order n, right? Oh, sorry, I didn't see that. Sorry. It was written.
I see. Yeah, I think it's right.
Yeah, sorry.
Okay, but then the subset actually has a natural map to x1 squared. So there's a map from x naught of n into x1 squared, which is a generic injection. We call it phi n. And what this does is phi n of a pair E, comma G. We need two elliptic curves, so the first one is going to be just E, and the second one will be E portioned out by this group G. Okay? So generically this is an injection, you can actually recover E and G from this. Sometimes it's not, and it's not precisely when, but when E has certain Cm, and you have extra endomorphisms, so you can't quite recover G from these two elliptic curves. Okay? That's sort of the image of, we define Tn, would be the image of Tn, and Tn is x1 squared, is a Hecke curve. And what is Tn? Well, it's precisely pairs of elliptic curves with a degree n isogeny between them. Degree n cyclic isogeny between them. You can specify in B and G. Okay? So one nice way to look at this is if you look at the map on the uniformizing spaces. So you can look at the map in the upper half plane to the upper half plane squared. So you can choose many different lifts of this because you're monodromy. But one nice lift you can look at, we call phi and tilde, send z to the pair z, comma, nz. Okay? And so it turns out that gamma naught n, if you act by gamma naught n here, you're acting by f to z, f to z over here. So it descends to a map between these two spaces, and it's exactly this map. And in fact, you can see pretty easily that E mod 1z has a cyclic degree and map to E mod 1. Let me just write this down. So the cyclic isogeny here is this map. Just sends an element tau to n times tau. So there's an isogeny between these two arbitrary curves. In fact, the degree and cyclic isogeny, the kernel is exactly 1 over n. So the subgroup generated by 1 over n is the kernel of this map C. Okay? Okay, and so this Tn has the property that it's sort of bialgebraic on the uniformizing map. Right, inside h squared, Tn is just some linear subvariety, just line w equals n times z. And down in x1 squared, well, it's hard to describe what it is, but it's some algebraic curve still. So it's algebraic in both worlds. So it sort of has this property that we'll be talking about with sort of subtori and Torban cosets. And so we say that an irreducible subvariety curve, I guess. Let me say curve. C. Next one squared is special if, so one of two things has to happen. Either there exists an n such that C is one of these p sub n's, or C is a fiber of x1, where this point P is a CM point. It corresponds to an elliptic curve with extra endomorphisms. Okay? And so then the theorem, which in this case is due to Andre, and so the base case what we're going to do is that if C in x1 has infinitely many CM points, then C is special. C is special. Okay? All right. So this is the same sort of formal structure as the base case of Lang's conjecture, and it's sort of the first case of the Underwood conjecture. So next time we'll discuss the statement of sort of how we generalize this.
X1 squared.
Sorry? Is it incorrect? Oh, x1 squared. Thank you. Anything else? Okay. Thanks.